Hello and welcome back to another higher mathematics video. Today we're going to continue our topic on differentiation, and we're going to keep looking at stationary points as we did in the last video, but today we're going to be talking about how to determine the nature of the stationary points. So in our last video we talked about stationary points, and we mentioned that if the derivative of a function, of a curve, is equal to 0, then we would say that the curve is stationary at that point. So we had examples here where we could see a stationary point can be given by a turning point, and it's very important that we notice whether this stationary point is a maximum or a minimum turning point, or a rising or falling point of inflection. Well, that's what we're going to do in today's video. We're going to show that if we have a stationary point, so if the derivative is equal to 0, we're going to be looking at whether we can tell if the point is a maximum or a minimum turning point. And this is what we call the nature of the stationary point. So how do we determine the nature of the stationary points? Well, we'll go through a little example here so we can work out if the stationary points of a curve are a maximum or a minimum. So let's say we had a curve that's given by the function f of x, and we'll say it's equal to 2x cubed minus 9x squared plus 12x plus 4. Now, as you can tell, this function would be very difficult for us to draw. It would be difficult to graph this function. So how can we determine the nature of the stationary points without having to sketch the graph? Well, we go through 8 very simple steps to work out the nature of the stationary points and how many stationary points exist as well. And I'll go through each of them right now very slowly with you. So for the first step, we just want to do a bit of differentiation. If you remember, we said stationary points occur when the derivative is equal to 0. So let's start by differentiating f of x. So we get f dash x, the derivative, is going to be 6x squared, take the power down to the front, minus 18x, and then 12 is going to be the bit at the end, and the 4, as you can see, is just going to go to 0. So this is the derivative. Now, the second step, as we mentioned a few videos ago, was to find the stationary values for solving for the derivative equal to 0. So as we said, the stationary points occur when the derivative is equal to 0. So we'll just write SPs occur when f dash x equals 0. So we would say that 6x squared minus 18x plus 12 is equal to 0. And you just need to factorize this to solve for x. So just a bit of algebra here. We can see we're going to have, in fact, actually we do have 6x, so we can actually take out a common factor of 6 here. So we'll do that first, I believe. We'll have 6, and then we'll have x squared minus 3x plus 2. This should make it a bit easier for us to factorize because we'll have 6, and then it looks like we're going to have x minus 2, x minus 1. And you can check that yourself to see that you will get 6x squared minus 18x plus 12 is equal to 0. And then from this we can see that either x is equal to 2 or x is equal to 1. Now these are just the x coordinates of the stationary points. We want to work out the y coordinates of the stationary points as well. Now, in this case, we just substitute 1 and 2 back into our function to find the y coordinates. So, step 3, which is find the y coordinates. So to do that, we start by finding f of 1. So this is when x equals 1. The function, technically the y coordinate, but we just call it the f of x coordinate. We're going to substitute in 1 into this, so we get 2 times 1 cubed minus 9 times 1 squared plus 12 times 1 plus 4, which is just going to give us 9, I think, because we'll get 2 minus 9 is minus 7, plus 12 is 5, plus 4 is 9, yep. And then we'll also find f of 2. So do 2 times 2 cubed minus 9 times 2 squared plus 12 times 2 plus 4. And I've already worked this out before, but it does give us 8. So we can say from these that we can work out the coordinates of the stationary points. So we know that the stationary points are, and it's always good to write this just so you know exactly what you've worked out here. So when x is 1, we get 9. So 1, 9 is a stationary point. And 2, which gave us 8, is the second stationary point. So the first 3 steps, which are arguably the steps we should already know how to do, is how to work out the coordinates of the stationary points. So we have worked at the stationary points by finding the derivative, setting it equal to 0, solving for x, and then finding the y coordinates. And this gives us the 2 stationary points. So the next few steps is where we work out the nature of the stationary points. And we're going to do this by using what we call a nature table. So for step 4, we will begin our nature table. Now the way you write your nature table is you start off with the left-hand column. So we're looking for values of x. Then we're saying for each x value that we've worked out, so for 1 and 2, we want to know what the derivative at this point is. And therefore we want to know what the graph is going to look like at this point. Now this all might sound quite confusing right now, but it will make sense when we start to substitute in our values for x. So we're going to create a little table like this. And we want to look at when x is going to approach the value 1 first. So this is what we're looking at first. And we also want to look at the graph when it approaches the value 2. So we write that like this. And what this basically means is the arrows going in and out of the numbers means the graph as it approaches the point where x is 1 and as it goes away from it, and the graph as it approaches 2 and as it goes away from it. So we've constructed our nature table. Now for step 5, we are going to calculate. We're going to calculate f dash x for the values in the table. So what we mean by this is substitute in 1 and then substitute in 2 into the derivative f dash x to see what we get for these values that will go underneath them. So for f dash 1, we find that we get 0, which is good because that's what you want to get. So we get 6 times 1 squared is just 6, minus 18 is going to give us minus 12, plus 12 is 0. So we get the value 0. Now that's good. We want to see zeros. Now when we substitute in 2, we find that we're going to get 6 times 2 squared is 4, times 6 is going to give us 24. 24 minus 36 is minus 12, and then plus 12 also gives us 0. So the derivative substituting in 2 is also going to give us 0. So this is very good because these zeros confirm that the stationary points exist at the points where x is 1 and x is 2. So for step number 6, this is where things might get a little confusing. We want to see what the graph looks like as it goes away from the coordinate 1 and as it approaches the coordinate 1. So what we do is we pick a value really close to 1 and then also just after 1 to take a look at what f dash of x is going to look like at that point. So for example, just before 1, we might look at the value 0.9, And just after 1, we might look at the value 1.1. I tend to do 0.1 after it. And for 2, we're going to look at the value 1.9 and 2.1. So what we're going to do in step 6 is we're going to substitute these 4 values into our derivative again. So we substitute it in like this. We're going to find f prime of 0.9. And when we substitute that in, we're not looking for the exact value it gives us. We're only looking to see if this gives us a positive or a negative number. Now I can tell you right now that when you substitute this into your calculator, if you were to give it a go yourself, you'll find that you'll get a positive number. So we want to write before the 0 that as it approaches 1, we have a positive value. Now we want to look at it with, I'm just going to put positive. Now we want to look at f prime of f dashed of 1.1, sorry. And we want to find out if that gives us a positive or a negative value. Now, as I have already done this before, I can tell you that it gives us a negative value. Now we're going to do the same for 1.9 and 2.1. So we look at f dashed of 1.9. Usually this will be in a calculator paper, and 2.1. And we find here that we're going to get a negative value and we're going to get a positive value. Again, we don't care. It's going to be some sort of weird number, but we just care if the sign in front is positive or negative. So here at 1.9 we have a negative, and at 2.1 we're going to have a positive value when we substitute it in to f dashed x. So for step number 7, we can now sketch what the graph is going to look like in this graph row. And we need to know that 3 things. The first thing is that a plus means that the graph is increasing. So it means that the graph is increasing. A minus means decreasing. And a 0 just means it's stationary. So what did we say increasing looks like? Well, we said it looks something like this. We said decreasing looks something like this. And stationary will just give a flat line like this. So we can sketch what these are going to look like. So when it approaches 1, we said at 0.9 it's going to be increasing. Then when it gets to 0, it's going to be stationary. And then when it gets to 1.1, it's decreasing like so. And we'll do the same over here. So as it approaches 2 at the point 1.9, it's going to be decreasing. At the stationary point, it's obviously going to be flat. And then as it leaves x equals 2, at 2.1, it's going to be increasing. And now from this, we can determine that because this looks like this, the graph basically looks like this in the first bit. As you can see, it's going to go up and then back down. Then we would say that this stationary point is a maximum stationary point. And this stationary point, as it goes down like this, we can say is going to be a minimum stationary point, or we call these turning points. So the last little thing we'll do, and I'll just do step 8 down here, is we would say that the coordinate 1, 9 is, so this is this one here, we can see it's going to be a maximum turning point. And we can say that for this coordinate here, which was the coordinate 2, 8, and we would say that this is a minimum turning point. So we'll say it is a min turning point. Now that was quite a lot, so what I'm going to do is I'm quickly going to run over it all again for you guys with a little example, and then with a little bit of practice you will get the hang of this and working out how to substitute in these values and basically how to use a nature table. Alright, so here's our first question. We are asked a curve, or told a curve has equation y equals x cubed minus 6x squared plus 9x subtract 4. And we are asked to find the stationary points on the curve and determine their nature. Now again, this will usually be in a calculator paper if we're asked to determine the nature. If it's in a non-calculator paper, you might just be asked to find the stationary points. But here we also want to work out their nature. So when you see nature, you know you'll be using our nature table. So the first thing we want to do is we want to find the derivative of the curve. That was our first step. Now this is already okay for us to differentiate. So we can just say that the derivative dy by dx is going to give us 3x squared minus 12x plus 9. Now again, we know that the stationary points occur when the derivative is equal to 0. It's quite important that you write this. Now, you could also say the stationary points exist, or you could say they occur, or they're basically the two words that you need to write. But this sentence is very important that you write this, because this explains what you're about to do next. Because what we do next is we take our derivative, 3x squared minus 12x plus 9, and we set it equal to 0. And then we solve for x to find the x values of the stationary points. So like we did in the example before, we can take out 3, like so, and then divide both sides by 3, obviously. We can now factorize this. We'll get 3, we're going to get x, we're going to have another x, and it looks like it's going to be 3 and 1, minus 3, minus 1. So from this, we know that x is going to be equal to 3, and x is going to be equal to 1. And if you don't remember how we did this, I know I didn't explain it in the example before, but because this is equal to 0, we know that either 3 is equal to 0, which is not true, so we're just dividing both sides by 3 here, or we know that x minus 3 is equal to 0, and when we solve for x, we get x is equal to 3, or x minus 1 is equal to 0, and when we solve for x, we get x is equal to 1. So our next step is to work out the y coordinates. So we say when x is equal to, let's do 1 first, substitute it into the curve with the equation y equals x cubed. So we'll get 1 cubed minus 6 times 1 squared plus 9 times 1 minus 4. And I'll just write this out here. We can see we're going to get 1 minus 6 plus 9 minus 4, which is simply just 0. And we also want to work out when x is equal to 3. So when x is 3, our y is going to be 3 cubed minus 6 times 3 squared plus 9 times 3, subtract 4. And when we do this, 3 cubed is 27, 6 times 3 squared is going to be 54, and then 9 times 3 is 27, and then minus 4, and we find that this is going to give us, 27's cancel out, so it's just going to be, the 27's added together, subtract the 54 cancel out, so it's just going to be minus 4. So from these two, we can determine that we have two stationary points. So we say our stationary points are, we make sure we use the right x with the right y, so that's 1, 0. And the second one is 3 minus 4. So that's the first half of the question by working out the two stationary points. But the next thing we want to do is work out the nature of these stationary points. And this is where our nature table comes in. So we know we're going to have our x values at the top. Then instead of f dashed x, this time we have the derivative dy by dx. And then we want to see what the graph is going to look like. So we'll form our nature table. Now you should always use a ruler for this, but I do not have one. And we'll just split it down here because we know we've got 2 points to look at. The first point we want to look at is when x is 1, and the second one is when x is 3. And also we want to look at as it approaches 1 and goes away from 1, and as it approaches 3 and as it goes away from 3. So the values before 1, we'll use 0.9, very close to 1, and just after 1 we'll look at 1.1. And then just before 3 we'll look at 2.9. Just after 3 we'll look at 3.1. Now we can start by substituting in 1 and 3 into our derivative, which is here. If we sub in 1 and 3 into this, we'll find that it should give us 0. I'll do it just down here though. So the first one, if we substitute in 1, when x is equal to 1, dy by dx is going to be 3 times 1 squared minus 12 times 1 plus 9, which is just 3 minus 12, which is minus 9, and then plus 9, which is equal to 0. And then when x is equal to 3, we get that the derivative is going to be 3 times 3 squared minus 12 times 3 plus 9. And we get 3 squared is 9 times 3 is 27. 27 minus 36 is going to be minus 9. And then plus 9 is equal to 0. So that's good that we get these two zeros. Just confirms that they're stationary points. Now if we substitute in 0.9 into this equation here, you can try it in your calculator, but I'll tell you when you substitute in 0.9 that you get a positive value. So it's going to be a positive number. And when you sub in 1.1 into your derivative, we'll get a negative value. And the same over here, when you substitute in 2.9, you'll find you get a negative value. And when you substitute in 3.1, you'll find you get a positive value. So now with these three things, we've got a positive, so it's going to be increasing. We have 0, so it's stationary. And then we have minus, so it's going to be decreasing. Then over here, we have minus, which is decreasing. 0, which is a straight line. And then positive, which is going to be increasing. So now we can see what the points or the curves of the graph will look like when it gets to these 2 points. So we can finish off by saying, so the coordinate 1, 0 is a maximum because it approaches at the top. So it's a max turning point. And we can say that the coordinate 3 minus 4 is well, it comes down like this, so it's going to be a minimum turning point. So there we go. That's one complete example where we worked at the stationary points and also worked out their nature. But we'll do another example just to get our heads around it. So I'm going to do one more example here just because it can be quite difficult to do these questions. There's a lot of working you have to do. It's quite easy to mess up along the way, and also just they're very big questions. So let's go over this next question. So we're asked to find the stationary points of y equals 4x cubed minus 2x to the power of 4. And we are asked to determine their nature as well. So let's begin. So the first step we know is to find the derivative, dy by dx. We're going to get 12x squared and then bring the power down to the front minus 8x cubed. Now again, it's very important we write the stationary points occur when the derivative is equal to 0. So let's do that. Let's set 12x squared minus 8x cubed equal to 0. And we can take out a common factor of 4x squared in this case. So 4x squared, and then we're going to have 3 minus 2x is equal to 0. So we've got 4x squared is going to be equal to 0 in our first case, which just gives us that x is equal to 0. And in our second case, we get 3 minus 2x is equal to 0, which we can solve to give that x is going to be equal to 3 over 2. So these are our two values for x. So now we want to work out the y coordinates of these x values. So when x is equal to 0, we just substitute in x to be 0, we get y, which we can already see is going to be 0, but we'll do it anyway. 4 times 0 cubed minus 2 times 0 to the power of 4. We can see it's just going to give us 0. And then also when x is equal to 3 over 2, we're going to get y is equal to 4 times 3 over 2 cubed minus 2 times 3 over 4 to the power of 4. And to do this, we can see that this is going to give 3 over 2, which is going to be 27 over 2, I think. And over here, we're going to get 3 over 4. This is going to be 81 over 8. So we're going to get minus 81 over 8. And then we can just work this out. It's going to give us 27 over 8. So a bit of working with fractions there. It's okay if you want to show more working. I've not done much working, but more working is always loved in exams. So we can say now that our stationary points are, the first one is 0, 0. And the second one, if I've done it right, is going to be 3 over 2 and 27 over 8. Okay, so we've got our two stationary points now. We're going to do a nature table. So we're going to have x, then we're going to have the derivative, and then we're going to be looking at what the graph looks like. So construct your nature table. Like so. And we're going to look at it as it approaches, as x approaches 0, and as x goes away from 0, which is the first one, and then 3 over 2 in the next one. Now we're going to pick values just before and just after. So just before 0, we've got negative, let's go for negative 0.1, and we'll go for positive 0.1. And then just before 3 over 2, well, 3 over 2, if you put in your calculator, is going to give you just 1.5. So you want to pick a value very close to that. We'll just go for 1.4. And just after, we'll go 1.6. Now, if we substitute 0 in, we can see we're going to get 0. So it's going to be flat. And if we substitute in 3 over 2, you can try this yourself, but you'll find that it is going to give you, not flat, sorry. It's going to give you 0. We do that in the bottom step. Now, if you substitute in negative 0.1, you'll find it gives you a positive value. And when you substitute in 0.1, you'll also find that it gives you a positive value. Now, we write this dy by dx here, so we know that when we substitute it in, we're substituting it into our derivative formula, which is this one here. And when we do the same over here, substitute in 1.4, we should get a positive value. And when we substitute in 1.6, we will get a negative value. So now let's sketch what the graph is going to look like. We have increasing, then we have flat. Now this time we have increasing again, so it's going to look like that at that stationary point. And then over here we have increasing, then we have flat, and then we have decreasing. I'm just going to put that a little bit lower. Now because this time it goes up, across, then up, we call that our point of inflection. Whereas this one here, we can see it goes up, across, and back down. So it's going to look something like that. So that's going to be a maximum turning point. And if you want to visualize that one there, it's going to go like that. As you can see, up, across, and up. So we would say that the stationary point 0, 0 is, and it's a rising point of inflection because it's not going like this. It's going like this. So it's going to say it's a rising point of inflection. Inflection. And the coordinate 3 over 2, 27 over 8 is a maximum turning point. And that is going to be our last example of the video. So as you can see, these questions are quite long. You have to do a lot of working, but they will always be worth plenty marks. So be sure to practice with the nature table, substituting in these values into the derivative and showing what the curve is going to look like. And therefore you can work out the nature of the points.